We now have time for discussions. There are a couple of questions here, and two of them are placed by Professor Hiroshi Kawase. One is addressed to Artie, and the other one is to Ricardo. But those are kind of combined question and comments. So I would like Artie and also Ricardo, if you can read it out loud and maybe make comments about what Professor Kawase is discussing about.
Well, so Professor Kawase has asked, let's see, one question. He says, it's nice to see your V&V exercises. I have one question, one comment. In your presentation, you showed that the simulated PGA is matched with the empirical formula without strong bias, but the simulation is done in the frequency range up to 4 Hertz. And I'll stop there because I didn't really consider the PGA for those lower frequency simulations, but we did in the high frequency when we go to 10 Hertz. And rather than belabor this point, I would just refer to the paper that came out in BSSA on the 10 Hertz simulations, which really point the need for handling site response effects, because there you have the competing effects of underestimation of the ground motion because we've assumed a minimum shear wave speed of 500 meters per second. And in low, 30% of the sites in the Bay Area in our simulation domain have a VS30 less than 500 meters per second. But then when you subject these weak soils to very high acceleration, they damp the high frequencies. So what we did was use the Bayliss and Abrahamson Fourier amplitude-based ground motion model to develop, which separate linear and nonlinear site response terms. And we evaluated that and showed that the application of that site response correction is a way to remove bias in high frequencies. There's basically a rotation of the spectra that occurs there. And then the comment is about, let's see, he says, comment is for future proposal. It is great to standardize the targets of the numerical exercises for validation. One caution of such exercise is that the source information before such 3D basin response comparison is not consistent with the 3D basin model used. Rather than it's based on a simple predefined 1D structure like the broadband platform, I think is what he's referring to, for example, so that it may not be perfect for the model validation. In other words, we need a built-in mechanism to continuously improve the source based on crustal models that we are comparing. Well, absolutely. I mean, we are using Graves and Pitarka, the broadband platform extensively calibrated this source model with 1D models, which are a great oversimplification. 1D models, in my opinion, should be quaint at this point and not something that we spend more time on unless we have evidence that the model or the region is truly plane layered. The point of what we're doing is trying to stretch the envelope to go to higher frequencies and use these models, which are calibrated in a 1D structure, and try to push the envelope to go to higher frequency. We've seen good consistency of our ground motion intensities in terms of median sense with using the Graves and Pitarka rupture model, and we'll continue to do that. And we're continually exposing problems with the source models by running these simulations. And Arben and Rob are continually making improvements. And my other panelists here probably have thoughts on this as well.
Thank you, Artie. Professor Kawase, you made excellent points. What I will add to what Artie mentioned is that, well, first of all, we don't, at least in my case, we don't do the whole thing, the whole circle. So we are not the ones who do the inversion of the source. Instead, we take the best possible source model that others can produce, and then we use that as input for the forward simulations, right? And then we point out what we see that source model is missing, in a sense, right? And then that obviously can be a result of the 1D, 3D discrepancy that you point out correctly. But it may also be because of other things, right? So what we do in that sense is to just try to be to do separate works so that there is independence in that sense, right? So that because the other way around, it is also risky, because if you do the same inversion with the same model that you use for the forward, then you probably go into a circle problem in which you are just producing the best fit out of improving your inversion, right? So there is risks. There are risks in both approaches. That's what I will say. And if it is up to me to choose, then I prefer that someone else do the inversion of the source, and someone else do the inversion of the tomography work for the velocity model, and then an independent group does the forward simulations for validation purposes, right? So, but I understand your point. Now, about the technical detail of whether the comparisons with data are filtered so that the match is in equal terms, then the answer is yes. Both the data and the synthetics are run through the same filters so that those comparisons are on equal terms. And then, yes, the smaller earthquakes probably have that higher variability involved in the results, and especially near the source, I will say. But then again, there are other factors that will get into the mix of everything when you go to the moderate size or large events, because perhaps nonlinearities matter more than in the small magnitude earthquakes. And if we haven't figured out how to get a good match for the smaller magnitude earthquakes, then when we get to the higher magnitude earthquakes, then we probably have even more factors that are more significant in other aspects of the comparison. So, but I agree with all the points that you made in your questions. It's just that it's a matter of finding some kind of balance among the many factors that influence the results.
Urban, is there time for me to make one quick comment?
Yes, of course, yeah.
So just picking up on the string from both Adi and Ricardo, I think the other important thing to keep in mind is that both source inversions and also crustal model inversions, whether it's through tomography or just travel time or full waveform tomography, they're also with different frequency components that are really the focus. So, for example, source inversions are low frequency, whereas actually the Graves and Pataka rupture generator, is fractally complex such that it generates all the way up to high frequencies. Also, in the 2010 paper of Graves and Pataka, there was actually discussion of how to generate the source for a past event or for a future event. And the idea with the past event, you can try and incorporate those source inversion features. And then Rob and Arbin kind of threw out that approach because they said, it's better actually just to use the geometry and the hypercenter and then generate the event in the same way you would do for a future event. And so I think that's really the important aspect there. The same is true for crustal models that are developed from 3D tomography. That's not going to have enough fine scale resolution. You're still going to have to add complexity through scattering and so on and so forth. So I think they are sufficiently decoupled that it's not a problem.
So I have one very short comment before letting Jack answer the question that Spasti asked. I think all is good. I mean, we're trying to understand where things are not working very well in terms of models, but we still don't have a good mechanism that feeds back this misfit results to actually the model themselves. So we stop there. And I think this is very, very, very challenging and very difficult job because we're not going to go back to do a high frequency tomography. I'm not advocating that, but there should be a kind of mechanism in the way we do things when we build a 3D model. We try to include a lot of information. So there should be another one that will take care of this misfit that we discovered in geographical regions. So yeah, Jack, there's a question for you.
Arben, and if I may, I think precisely because of what you said, is that being able to do this in an automated way is so important. What most of the people have shown today and yesterday in terms of large scale simulations are usually efforts that take a lot of energy, and then to be able to reproduce them in equal terms is not so easy. And so that's an important aspect of the computational magic behind.
Yeah. Jack, I guess you have an answer?
Yes, so the short answer is
people are asking for new codes.
Yeah, we do have some code up. I just clicked a response in the with some links, but I guess it went into the answers category when I clicked that. So yeah, so we have some code for kind of aggregating up the observations and then doing the parametric fit. So that's one repository, and then we have a second repository for doing that clustering analysis that I spoke about in the middle of the presentation, where you take this correlation graph and try to partition it out. There's a separate repository for that as well. So both links are on my website, kind of adjacent to the associated papers, but I also just put the repository links in the Q&A box as well for convenience. So hope somebody finds it useful. We'd be very pleased.
I have a question for Jack. I really like this analysis of the spatial correlation. And have you, does the empirical, does the existing station database support such analysis with empirical data in some region? I mean, you showed a little bit in Taiwan. Yeah.
That is an excellent leading question. I was actually chatting with Brendan Bradley about that. So New Zealand actually is the place in the world we found to be best fit, because Christchurch and Wellington both have relatively dense networks that have seen repeated strong earthquakes. So it's not an exact analog because the ruptures still vary, but we did go through the process. So actually worked under advising of Brendan as well on this. We went through the process of taking the observations, computing residuals per event, and then taking paired observations. You can get a half dozen to a dozen paired observations at some of these stations, and then pulling it apart and looking for patterns of correlation. So there, it's not going to be source effects because the sources are mixed, but you can see some geologic factors and sedimentary basins in Wellington and things like that playing a bit of a role. I don't know if Brendan wants to add any more. He helped a lot with
that. That then the really interesting follow-up that's yet to be done is, do you see the same paired spatial correlations with simulations? Can we reproduce that same systematic deviation of pairwise correlation from the sort of ergodic, stationary, and isotropic correlation? So I think that will be interesting.
Yeah. I mean, there's good analogs to the non-ergodic hazard and site-specific analysis, and but it's even tougher because of this need for paired observations, and we're really at the infancy of this. But I think the chance to infer causality from simulations and then benchmark it against empirical data when we can, there's a lot of opportunity to better understand kind of what's driving these scattering and what's driving the patterns of amplitudes that we observe.
Yeah, one way I like to think about it is, if you have n ground motion observations, then you compute a certain level of metrics, and so you have n times those metrics. When you start to use spatial correlations, you get n squared. So the amount of data that you have really goes up significantly to constrain the simulations. Now, not all of those are interesting, because with large separation distances, those spatial correlations are not informative, but it still drastically increases the insight that we can get from the simulations and the observations. We've lost our host.
We're experiencing a heat wave in Northern California, and I know that the lab, Livermore Lab, had a power outage, so I thought it was just me.
Oh, I see.
Sorry, looks like Hiroshi Kawase would like to speak. Maybe we can. Hiroshi-san, you could speak now.
Can I make a comment with Professor Blendon Bradley about the difference between the frequency range of source determination and the simulation? If you guys are extending the simulation into high frequency up to 10 Hertz or so, then the source representation should be conform with that kind of frequency range. But currently, the routinely determined source is a relatively long period range, so that referring to that kind of source is not appropriate for the simulation in high frequency. That's my point. So that now for you guys in California, it is time to determine the source spectra routinely for earthquake less than 5 with the 3D velocity structure that you are agreed with to use for this kind of source inversion routinely, and then you can use independently determine these source spectra for simulation. That makes sense as Ricardo's comment for independence between source determination and broadband strong motion simulation. That's
Yeah, I completely agree with you. Yep. And so basically the synthetic rupture generators usually are calibrated to source inversion studies at those long wavelengths where they know that they contain information, and then they have some sort of fractal complexity to shorter wavelengths where they know the source inversion studies don't have the information currently. But certainly if those source inversion studies can go to higher frequencies and smaller wavelengths, then the assumptions in that fractal complexity can become better constrained.
Okay, everyone, it's a excellent discussion. Thank you all. We are quite a bit into the break, so we'll reconvene in 2 minutes and start with the next session moderated by David McCallum. Thank you all.
Yeah, I apologize. I had some problem with my connection here. That's why that.
Oh, no problem, Arvin.
All right.
Yeah.
Thanks.
We just ended the session.
Okay.
We'll reconvene in a minute.
Perfect. Thank you.
Okay. Bye. Thank you, Arvin.
Thank you.
Thank you, Ricardo.
Great presentations, everyone.